Balloon 4-2 Weather Theory and Reports. Let's talk about the dynamic boundary zones where air masses collide, the fronts. These are the dividers between two air masses, and they come in four major types: cold, warm, stationary, and occluded. Imagine them as the meeting points of actors on our atmospheric stage, each playing a role in the weather narrative. Starting with the cold front, it's like the cool kid on the block leading an advancing mass of cold air, pushing its way in and shoving the warmer air aside. Cold fronts move swiftly like a snowplow sliding under warmer air. As they charge forward, the denser cold air forces the warmer air to rise, creating clouds, and depending on the stability of the warmer air, you might get cirriform or towering cumulus clouds, or even ominous cumulonimbus clouds. Rain showers, thunderstorms, and a sudden drop in temperature often accompany their entrance. After the cold front exits, the skies clear up, leaving behind gusty winds and cooler temperatures. Now picture a fast-moving cold front. It's like the overachiever of the cold front family. Pushed by intense pressure systems, these fronts move rapidly, creating a narrow band of weather concentrated along their leading edge. If the warm air they overtake is stable, you might see overcast skies and rain ahead of the front. But if it's unstable, buckle up for scattered thunderstorms and rain showers. A squall line, a continuous line of intense thunderstorms, may form along or ahead of the front, presenting a serious hazard to pilots. Behind a fast-moving cold front, the skies clear in a hurry, leaving behind gusty winds and colder temperatures. These atmospheric fronts are like plot twists in our weather story, each bringing its own set of challenges and surprises for pilots and weather enthusiasts alike. Let's dive into the world of warm fronts, stationary fronts, and occluded fronts, the supporting characters in our weather narrative. First up, the warm front, the trailing edge of a retreating mass of cold air. Unlike its swift counterpart, the warm front moves at a leisurely pace, typically 10 to 25 mph. As it advances, it gracefully slides over the cooler air, gently nudging it away. This front carries warm air with high humidity, creating a symphony of cirriform or stratiform clouds and fog along its path. In the summer, you might even witness the performance of cumulonimbus clouds, bringing light to moderate precipitation in the form of rain, sleet, snow, or drizzle. As the warm front approaches, the barometric pressure drops until it passes, leaving behind stratocumulus clouds, rain showers, and improving visibility. Next on stage is the stationary front, a boundary where air masses are locked in a standoff. While the surface position remains still, an uplift of air may occur along the front, giving rise to stratiform clouds or, if conditions are right, cumuliform clouds with thunderstorm potential. Now enter the occluded front, a plot twist where a fast-moving cold front catches up with a slow-moving warm front. Depending on the temperatures at play, we have two scenarios. In a cold front occlusion, the colder air overtakes the cooler air, creating a blend of weather found in both warm and cold fronts. In a warm front occlusion, the colder air ahead of the warm front forces it aloft, potentially leading to more severe weather, including thunderstorms, rain, and fog. Picture these fronts as dynamic elements in our atmospheric screenplay, influencing conditions and challenging the characters, be it pilots preparing for ballooning activities or weather enthusiasts decoding the skies. They add layers of complexity, making each weather episode a unique experience. Picture yourself gearing up for a mountain journey. It's thrilling, no doubt, but it comes with challenges. Understanding the weather becomes your first line of defense. So what's going on in the atmosphere? Pressure and temperature changes stir things up, creating vertical and horizontal motions, ascending and descending currents, and wind, respectively. Both types of movement are crucial, affecting takeoff, landing, and in-flight operations. More importantly, these atmospheric motions, or atmospheric circulation, drive weather changes. For a balloon pilot, mastering wind and current circulation patterns is key. Balloons navigate by interacting with different layers of wind and current. With knowledge of the Coriolis force, pressure gradient force, and surface friction, pilots can predict their potential track with high accuracy, landing at a predetermined point. That's the mark of a skilled and safety-conscious balloon pilot. Now let's talk about atmospheric circulation. Three forces, the Coriolis force, pressure gradient force, and surface friction, work together to set the wind in motion. Picture the Earth with its curved surface rotating on a tilted axis while orbiting the Sun. This rotation causes areas of low pressure over the equator and high pressure over the poles due to temperature differences. Solar heating makes air less dense, causing it to rise over the equator. The low-pressure area lets high-pressure air flow from the poles toward the equator. As this warm air moves, it cools, becomes denser, and sinks back towards the surface, creating a high-pressure area. The Earth's rotation then breaks this general flow into 3 distinct cells in each hemisphere. In the northern hemisphere, warm air rises at the equator, moves northward, and is deflected eastward. By the time it's a third of the way from the equator to the North Pole, it shifts from moving northward to eastward, forming the northeasterly trade winds. Similar circulation patterns create westerly winds between latitudes 30° and 60° and from 60° to the poles. These circulation patterns are further influenced by seasonal changes, variations between continents and oceans, and other factors like frictional forces due to the Earth's topography. Friction near the Earth's surface, within 2,000 feet, slows down the moving air, causing some diversion from its path due to reduced Coriolis force. Let's explore the fascinating realm of the Coriolis force, an imperceptible influence that orchestrates a celestial performance. While it might go unnoticed in our day-to-day movements, its impact is profound on larger entities like air masses and bodies of water. Consider the Coriolis force as a cosmic conductor, gently steering air to the right in the northern hemisphere. This subtle nudge transforms a straightforward trajectory into a graceful, curved path. The elegance of this celestial ballet intensifies at the poles, gradually diminishing near the equator. Importantly, the speed of the movement, or rather the air's circulation, influences the force's magnitude. In the northern hemisphere, Earth's rotation adds a captivating movement to the air's circulation, directing it gracefully to the right and shaping the overall choreography. Breaking down the Coriolis force, the force acts perpendicular to the air's flow. It guides air to the right in the northern hemisphere and to the left in the southern hemisphere. The poles witness the most pronounced effects, while the equator experiences a more subtle influence. The force requires wind to manifest its expression, intensifying with higher wind speeds. Collaborating with other forces, it contributes to diverse air circulation patterns globally. Now let's transition to the dynamic interplay of pressure gradient, a theatrical performance featuring pressure differentials between high and low pressure areas. Envision this as the atmospheric stage where wind speed takes center stage, intricately tied to the pressure gradient. When isobars cluster closely, cue the entrance of vigorous winds, widen their spacing, and a gentler breeze graces the stage. High-pressure systems play the role of majestic hills, while low-pressure systems assume the persona of valleys. The pressure gradient force acts as the unseen conductor, orchestrating the atmospheric symphony and encouraging air to gracefully flow from high to low-pressure regions. It's the force that maintains rhythmic equilibrium on the atmospheric stage. Now let's delve into the intricate dynamics of surface friction, a crucial player shaping the flow of the wind. Envision the Earth's surface as a textured stage, introducing resistance that not only slows the wind, but also influences its intricate movements. As winds diverge from highs and converge near lows, the rough terrain below dictates the choreography. In this atmospheric interplay, surface friction plays a pivotal role, altering the Coriolis force with its nuanced influence on wind speed. Picture the Earth's surface as a textured stage, introducing an element of resistance that not only decelerates the wind but also orchestrates intricate wind movements. As winds diverge from highs and converge near lows, the rough terrain below dictates the choreography. In this atmospheric ballet, surface friction plays a pivotal role, altering the Coriolis force with its nuanced influence on wind speed. As the wind encounters the Earth's rough surface, it experiences a momentary disruption in the delicate balance. The Coriolis force, intimately tied to wind speed, momentarily shifts, setting the stage for a graceful reconfiguration. Air now flows at an angle across isobars, a journey from high pressure to low pressure. The interaction varies in style, with angles ranging from a gentle 10° over the ocean to a more pronounced 45° over rugged terrain. The profound impact of surface friction extends close to the ground, but its effects ascend, carried aloft by the whims of turbulence. The wind, under the influence of friction, gracefully slows down up to an average altitude of 2,000 feet above ground level. Beyond this threshold, friction's influence rapidly wanes, becoming a negligible force. At altitudes above 2,000 feet, the wind flows parallel to the isobars, engaging in a harmonious interaction with the atmospheric elements. Now let's shift our focus to wind patterns, where the air plays out its eternal quest for equilibrium. With an inherent inclination to move from high to low-pressure regions, air embarks on a journey deflected by the Coriolis force. In the northern hemisphere, this orchestrated flow takes on a clockwise rhythm, circling areas of high pressure in what is known as anticyclonic circulation. Contrastingly, low-pressure zones beckon air towards them, initiating a counterclockwise or cyclonic circulation. High-pressure domains marked by stable, descending air usher in favorable weather conditions. On the flip side, low-pressure areas drawing in rising air set the stage for instability, often bringing clouds and precipitation. In this atmospheric interplay, the movements of air govern the symphony of weather, with high and low-pressure systems dictating the tempo of the performance.